Okay, let's see another example of a linear first order differential equation. So this is 20 on page 40, and if that's really what it is, then I expect it to either be like this, or I expect to see that I can transform this into that. There's the standard form of a linear first order differential equation. Y prime plus some function of t times y equals some other function of t. And with this, we're not quite there. So that would be easy to fix, wouldn't it? If we just divide by t, then we'll get exactly that form. Okay? So I'll get, if I do that, if I divide everything there by t, I'll get y prime plus, let's write t plus 1 over t, y, and then that's just going to be 1. Okay, well that is like this. I mean, I say h of t right there, but h of t could be a constant function in t. There's nothing wrong with that. All right, now, you remembered that the whole key with solving a linear first order differential equation, it looks like so, is the integrating factor. The integrating factor would be e to the power, which is the antiderivative of that, all right? This thing. So what's the antiderivative of that? T plus 1 over t. E should be taken to that power. There's your integrating factor. For the sake of integrating that, I'll reduce t plus 1 over t. Let's say 1 plus 1 over t. All right, so however that works out, that's the integrating factor. That's going to be, well, okay, that's t. That's what the 1 gives me. And this I get to say is natural log of t. Ordinarily, I might say natural log absolute value of t, but it was given that t is positive, so I don't have to worry about that. So what's that become? Laws of exponents are in play here, and I get that. And so I guess we would say t e to the t power. So that's your integrating factor. That's what you want. Now, say you took our standard form, like this, and multiply everything on both sides by that. That's how you use the integrating factor. If I do that, I'll get t e to the t power y prime. Okay. There, let's say e to the t power t plus 1. And then times y. And then t e to the t power. Okay, so I write this down. I guess you could skip this. If you do this right, this part always works out the same way. Every time it will work out that the derivative with respect to t of y times the integrating factor should be equal to that. Okay. Now, we could verify that. I mean, obviously, you're going to get y prime by the product rule times t e to the t. Then, to take the derivative of this secondary thing, t e to the t, we would have to use the product rule with that. But you could verify you get this, and then times y. So, it's really true, and it's going to work that way if you do it right. Now, say we integrate both sides. Okay, then it's a given that integrating with respect to t will give us this on the left. That's me verifying that it's the derivative. I know it's going to work out that way. That's the whole point of this method of solution, is that that happens. And then I would have to say, by some means, what the antiderivative with respect to t that is. Okay, now, about that, I mean, I guess it's always an issue how you do that. We might appeal to the formula sheet. There's countless methods of integration that we can use, but this one is integration by parts. We have already seen integration by parts several times, so let me just, I'll tell you what you'll get. You get t e to the t minus e to the t plus our constant. That's what integration by parts is going to give you from that. All right. Okay, now it seems like I'm one step away from an explicit solution, y is a function of t, if I divide by this. Okay, so if I divide by t times e to the t power, this will be a 1. This will become a negative 1 over t. And for that, I guess, let's say ce to the minus t over t. Okay. All right. Now, there's our general solution. General because that constant is undetermined. I have no way to tell you. I would need an initial condition to tell you what that is. So hence the general solution.